For months, 3I Atlas was treated as just another interstellar curiosity, an unusual visitor passing through our solar system, interesting enough for papers and observation time, but still comfortably labeled as a comet. That interpretation is no longer stable. As more data arrives from James Webb, Hubble, ground-based observatories, and deep space tracking networks, the object is refusing to behave like anything we understand. It is smaller than early estimates suggested, yet brighter than it should be at its distance. It is surrounded by an expanding envelope of dust and gas, and it is changing in ways that do not match standard comet models. Even its motion toward the inner solar system appears inconsistent with what solar heating alone can explain. What has made this case so unusual is not a single anomaly, but the stacking of many. Each layer of observation introduces a new inconsistency. And when those layers are combined, the picture becomes far harder to simplify than anyone expected. Early orbital reconstructions already hinted that 3I Atlas might not be a simple irregular body. Its light curve and trajectory suggest a teardrop-like geometry rather than a loosely bound spherical nucleus. That shape matters because it introduces asymmetries in how sunlight interacts with the object, how jets form, and how material escapes its surface. A non-uniform structure alone could explain some irregularities, but not what comes next. Astronomers then identified additional objects moving in close association with it. These companions do not behave like typical cometary debris. They do not disperse chaotically, they do not evaporate at expected rates, and they do not share identical acceleration patterns with the main body. Instead, they remain clustered, maintaining relative positions over long observation periods. That is the first major tension point. Classical comets shed material that spreads out. Here, the system appears to retain structure. This is reinforced by the most precise measurement yet recorded, a repeating brightness cycle of 16.16 hours. The periodicity is extremely stable across multiple datasets. It is not approximate, and it is not drifting. Something within the system is producing a rhythmic signal that persists as the object travels through space. The simplest explanation is rotation exposing active regions, but even that model struggles to account for the consistency and the way the entire coma responds in sync with the cycle. Instead of random outgassing, the system appears to pulse, as though different regions activate in sequence. When Hubble observed 3I Atlas in higher resolution, the results narrowed the mystery further. The nucleus appears surprisingly small, around a few kilometers across, yet it drives a coma and tail structure far larger than expected for an object of that size. In standard comet physics, sustained activity of this magnitude would require either a much larger nucleus or a rapidly depleting volatile reservoir. Neither fits the observed stability. Even more puzzling is the split behavior of the system. One component of the structure responds clearly to non-gravitational forces, while other parts remain unaffected. That suggests that not all material in the vicinity of the object is physically coupled in the same way. In simpler terms, different parts of the system are behaving as if they belong to different physical regimes. Infrared and optical imaging also revealed a clear separation between dust and plasma tails, confirming intense solar interaction. But what stands out is the persistent anti-sunward structure that forms under certain conditions. Instead of behaving like a typical tail pushed away from solar radiation pressure, part of the structure appears to align sunward in a stable, organized configuration. This is not expected under classical comet dynamics. The most consistent interpretation is that a population of larger fragments is reflecting sunlight in a way that creates the illusion of a structured tail, rather than a diffuse gas flow. This leads to one of the more uncomfortable implications. What we identify as the coma may not be the object itself, but a surrounding layer of material dominating its visible signature. If the nucleus is partially obscured by a swarm of reflective fragments, then much of what telescopes observe is indirect light rather than direct surface emission. At this point, scientists are forced to consider whether 3I Atlas is a single object at all. The presence of persistent companions, the structured brightness cycles, and the layered emission behavior suggest a more complex system. One possibility is that the object is shedding solid fragments that remain gravitationally or dynamically associated, forming a loosely bound cluster rather than a single nucleus with debris. The most debated feature remains the 16.16-hour pulse. Rotation alone cannot fully explain the consistency of the signal across multiple instruments and wavelengths. The pulse affects not just brightness, but the distribution of gas and dust around the object. Jets appear to strengthen and weaken in phase with the cycle, suggesting internal regulation rather than random surface collapse. This is where infrared data from James Webb becomes critical. Spectral analysis shows a composition rich in carbon dioxide and complex organic molecules, with relatively lower water content than expected for a typical comet. This is significant because most solar system comets are water-dominated. A carbon dioxide-driven system implies formation under colder and chemically distinct conditions, likely outside the environment where most known comets originate. More importantly, the energy driving the activity appears to originate below the surface layer. That means sublimation alone cannot explain the sustained emissions. Something deeper is contributing to the outflow, whether through structural layering, trapped volatile pockets, or internal mechanical stress. When all observations are combined, a more structured interpretation emerges. Instead of a passive icy body gradually evaporating, 3I Atlas behaves like a layered object with internal complexity, surrounded by a dynamically evolving cloud of material that does not behave uniformly. The swarm of fragments, the pulse-like emissions, and the asymmetric acceleration all point toward a system that is internally organized rather than randomly eroding. One of the more speculative, but increasingly discussed, possibilities is that 3I Atlas is a fragment of a larger differentiated body, ejected from another star system. In that scenario, it would not be a primordial comet, but a remnant of planetary crust or icy mantle material that survived a violent ejection event. This would naturally explain the unusual chemistry, internal activity, and structural cohesion of the surrounding fragments. Such an origin would also explain why the object behaves differently from typical solar system comets. It was not formed in the same environment. Its structure would reflect geological processes from another planetary system entirely, preserved through interstellar travel. In that context, the swarm is not debris from decay, but remnants of that original structure, material that remained loosely bound after ejection and is now interacting with solar radiation for the first time in billions of years. As the object continues its approach toward the inner solar system, particularly near Jupiter's gravitational domain, small changes in non-gravitational forces could significantly alter its trajectory. That makes this phase especially important for long-term tracking, since even minor asymmetries in outgassing or fragmentation could shift its path noticeably. Despite all uncertainty, one conclusion is becoming harder to avoid. 3I Atlas is not behaving like a standard comet in any simple sense. It is a composite system with internal structure, layered composition, and dynamically linked components that respond in coordinated ways. Whether that ultimately represents an unusual natural fragment, a rare form of interstellar debris, or something even more complex, the implications remain the same. Interstellar space is not empty. It carries structured material capable of surviving long journeys and arriving in our system still dynamically active. 3I Atlas may fade from view in time, continuing its journey back into deep space. But the questions it raises will not fade with it. Because if one object like this can enter our system with such complexity intact, then it is no longer safe to assume that interstellar visitors are simple, dead, or uniform. They may be fragments of entire worlds, carrying with them traces of distant planetary histories we are only beginning to recognize.